Hello students, nice to see you again in this video. Yesterday we were seeing about the first introduction of circular motion. We saw the definition as well as we saw two more definition, that is angular displacement and angular velocity, and the relation based on that we saw. Also we finally ended with the definition of centripetal force. Today we are going to see from page number 302 the examples producing centripetal force in a daily life, and there are three different derivations we'll be doing. This is an example, but it will be coming out as an expression and a derivation, so please understand this one carefully. These are all very important questions. So let's start. The first thing is bending of cyclist in a curved road. So you take a cycle and you're very happy about it to ride in a straight road. You keep on going ahead, then there is a curve, or maybe there is a U-turn. So what do? You just go to this U-turn and straight away you take a turn, but you will see yourself bending towards the center. Have you seen the way in which you will see the motorcyclist when they are doing the bike racing in a curved path? The motorcycle will be coming very much speed, and this guy will be riding the motorcycle, and you'll find that he will be leaning this direction. You'll be leaning more. Some of them really lean so much. This is the one, and you lean so much, and they keep the legs also sometimes like this. They'll go. This is the actual thing. They lean quite a good angle here, right? So the wheel will be leaning here accordingly. Why they lean like that? What is the necessity? Can they be straight? So whenever they are negotiating a curved road, even a cyclist, so they have to really lean towards the center. So consider a cyclist who is going like this. So now we are just drawing a wheel of a cycle. It is a cross-sectional view. So, and this is the way, and this is the handlebar. So a cyclist is coming and it's a curved path. The cyclist is already bent with an angle theta. So when the cyclist is bending on an angle theta, you will find the normal reaction is acting in this direction. Normal reaction acts in this direction here. So if you try to make a line like this, you will find the theta will come here like this. If theta is coming like this, what is this direction? It is going to be r sine theta. And what is this direction here? This is going to be r cos theta. And what is this one? Acting downwards. That is the weight of the cyclist as well as the cycle also. So it's going to be acting downwards. Now this is a curved path. The entire path is a curved one, and he is just making a kind of a negotiation. The cyclist is not straight, he is just bending towards the center of the circle and negotiating the curve. So you can write down few lines. Consider a cyclist going on a circular path, of radius r. It is circular path of radius r. If theta is the angle he bends, from the vertical, the normal reaction acts along the wheels can be resolved into two components. Normal reaction can be resolved into two components. So along horizontal, r sin theta. Now r sin theta will be contributing to something. What is the r sin theta will be contributing? Is it will be contributing to the centripetal force. It is mv square by r. R sin theta will be contributing to the centripetal force. Along the horizontal, r sin theta will contribute to the centripetal force. And then along vertical, what is that one? Along vertical. So maybe before this itself we can write this one, centripetal force. So you can write it as r sin theta is equal to mv square by r. Equation number 1. Along vertical, r cos theta acts opposite to mg. So r cos theta is equal to mg. Equation number 2. So we find this entire thing. Now if the cyclist is coming straight, if he is going straight like this, suppose this is a cyclist, he is just riding straight and with his handlebar like this, what happens? Normal direction is the top, mg is right down, straight downwards. Since it has bent, now the cos theta component and sin theta component has come. Now both of them, it has to be balanced with the force. So r sin theta will be balancing with the centripetal force. R cos theta will be balancing with the weight of this body. So it is a balanced force here like this. Now dividing 1 and 2, you will get this answer. 1 divided by 2. So r sin theta upon r cos theta is equal to mv square by r upon mg. It cancels out, r cancels out. So what is the next line you will get here is tan theta is equal to v square upon rg. Right? So theta is going to be equal to tan inverse of v square upon rg also. That's also a way you can write. Now, what determines the velocity? What determines the velocity and the theta value? So a cyclist is coming straight like this. He can come straight like this. In that way, theta is 0. So he can go as much as velocity as it could be. He can go in a very high speed also. But when he is going on a circular path, when there is a radius which is there, now when there is a radius which is there, definitely it depends, the angle makes it quite important. So the first observation is, the point number 1 is, when velocity is more, he comes in a high velocity. When velocity is more, then theta also should be more. He should bend so much, then only he will be able to be safe. So you can write down, when velocity is higher, then more bending should be negotiated. That's the reason you see the racing bikes, very high velocity, more angle they bend. Right? Number 2. The second thing is, for greater radius, when r is increased, look at this one, when r is increased, when bigger radius is there, theta can be less. That means more the radius, greater radius, then theta is less. If you are going on a sharp turn, very small radius, and you are going for a long big curve, it is a large radius. Look at this radius, this is this radius. Here you can go in high velocity, no problem. Here you cannot go in high velocity because it's a very sharp turn. Then the theta should be much higher because this radius is less. When radius is more, you can have less theta value. If it is a less theta value, you can definitely go on higher velocity. So that makes it quite a kind of an combination together. Alright children, with this we come to the end of this particular thing. You can refer to the book and read the whole thing, so how it makes it. Now also the centripetal force, it is contributed mainly to the r sin theta, also it contributes to the frictional force. So the frictional force between the tires and this one, it matters a lot. That will also contribute to the centripetal force. Okay, let's go to the next question, next example here. It is in the next page. Car on a level circular road. So there is a circular road. It's not a cyclist now. There is a car is now traveling and coming in the circular path. In that case, how it should be, how much velocity he can go. So that also we will be trying to find out in this one. So we see a car traveling on a curved path like this, and maybe this is the radius. So if we take this is the radius of the thing, maybe it can give it a small r as a radius from the center. So you can have to make a wheel of the car like this. So the car has a wheel, and so you're just making the top section of the car. So he's sitting here and he's coming. You're able to see a vintage car coming up like this. Maybe you want to slope it a little more, you can do that. So okay, so what are the various components when the car is coming on a leveled path? He is just coming in this direction. So this is mg, we already know this one. And here, this car, this wheel will be exerting a reaction of R1. This wheel will be exerting a reaction of R2. Whenever the car is going in a higher speed like this, now remember, this car, according to the Newton's second law, it is supposed to go in the straight direction here like this. It will be coming like this, going in this direction. But it has to make a curved path. So the steering wheel is moved. Even though the steering wheel is moved, the car can go in the same direction here itself, in this direction, because the steering wheel is moved. Now which one will help is the frictional force. The frictional force will be F1 here, the frictional force will be F2 here. It will try to pull this one in this direction. Otherwise, though no frictional force means it will slip. When it slips, then straight away it will go like this. If you are traveling in a very muddy clay soil, you'll be able to see this car is not going straight and it will just going the curved path, it will go skidding outside. There's a high possibility of skidding outside. Frictional force between the car, tires as well as the road will make this car to be in this place. So friction force is very important. Normal reaction. The total normal reaction which will be coming is R1 plus R2. So let us start with the basic things here. Consider a car of mass m traveling in a circle of radius small r. Traveling in a circular path of radius small r. So the weight of the car mg acts vertically downwards. The normal reaction R1 and R2 of both the tires act upwards and upwards. The frictional force F1 and F2 acts towards the center of the circle. So to negotiate a curved path, it is always requiring a centripetal force. The centripetal force always, it will be taking a help of something else. The force will come through something else. The centripetal force will always look for something that can contribute. Which is contributing now? The frictional force is contributing the centripetal force. So the frictional force F1 and F2 acts towards the center of the circle. Okay, on the tires, or you can say between the tires and road. So total frictional force, how much it is? Total frictional force is equal to F1 plus F2. So these two frictional force F1 plus F2 will be together acting. Now in other words, you can say F1 is going to be equal to mu times of R1, it is mu s, and F2 is going to be equal to mu times of R2. The next line is along the vertical. Normal reaction, capital R, is going to be equal to R1 plus R2. So R1 plus R2 is going to be equal to M into G. So what do you find here as? So the frictional force, the total frictional force M1 plus M2. So from here we will write again total frictional force. What is the total frictional force? F1 plus F2, which is equal to mu s R1 plus mu s R2, which is equal to mu s, you take it outside, R1 plus R2. So what is R1 plus R2? It is mu into mg itself. So that's what you get here, right? Now this mu into mg, so total frictional force is mu times of mg. I already told the frictional force contributes to what? Contributes to centripetal force. The frictional force contributes to centripetal force. So F now contributes to centripetal force. Now look at this one. It's quite important to finally write this last expression. It's very, very important. Still this much, it's pretty simple. Now frictional force always, no, it is a self-adjusting force. You already know. So more the force this side, this also frictional force also will increase. Higher the force, friction also will increase. At one particular time, beyond a particular force, frictional force will be kind of coming to a limited value. So whenever you are negotiating a circular path, remember one thing, your force that you are exerting outside, it should be definitely less than the frictional force. If this force is greater than the frictional force, you will be away, you will be slipping away, and the car will topple down. So the safe negotiation always means the external force should be much less than the frictional force. It should be a safety zone. So the frictional force should be much greater than or less than the centripetal force, that is mv square by r. If centripetal force is more, then the car will be, if the velocity is more, centripetal force will be more. If the velocity is more and centripetal force is more than the frictional force, then it will come completely slipping out and the car will not be able to be on the track. So the main important equation which finally concludes this whole thing is frictional force should be much greater than the centripetal force. So what is frictional force? Already we saw it is going to be this value, mu times of mg. So it is going to be mu times of m into g should be greater than equal to mv square by r. Mass gets cancelled out, right? So mu times of g should be greater than equal to v square by r. So finally, what do we conclude now? V square should be less than or equal to, this r goes that side, it's going to be equal to mu times of rg, which also implies, we can write it as v is less than or equal to under root of mu rg. So that is the final conclusion of the velocity formula. So how much maximum velocity you can go depending on the radius of the curved path. If the radius of the curved path is so very sharp, then the danger sign will be there. Go slow, go only 20 kilometers per hour. Why the 20 kilometers per hour? It is calculated because of the radius and the frictional force they are able to see in the road and the tires. So the road and the tires already mu is there fixed, r is fixed, and velocity also they can fix. Somebody says no, I will go on a high speed and I will try. You go on a high speed and skid and fall down. That's the reason many of the accidents take place in the curved path. They are unable to have control over the thing because the velocity is very high. So with this we come to the conclusion. I'll just go quickly through the whole thing. When a curved path the car is negotiating, it will be thrown away by a force. It will be skidding away. But the frictional force will try to keep it inside the track. So the total frictional force F1 plus F2 will be equal to the mu s and mu r2. It will be equal to mu into mg. So this is the total frictional force. Now with this is the frictional force which is there. Depending on the mass, depending on the coefficient of friction. If the greater the mass, more frictional force will be there. So remember, your velocity, the velocity you are negotiating, it should not exceed this value. You multiply the mass, you multiply the g 9.8, you multiply the mu value, you will get a value. Your value in which the way in which you are coming here, the centripetal force, it should be less than this value. Remember that. You are shooting beyond this value, then the car will not stay in the track, it will slip. So the friction force should be greater or equal than the centripetal force. So mu mg is greater than equal to mg because mu mg is the friction force. And here it is there. So maximum velocity, the velocity it's going to be equal to mu rg under root. That's a value. Alright, with this we conclude. We'll go to the next part of it. Before going to the next one, you have to write it as maximum. This is the maximum value. You can see in the book also it is written the value of V, it should be maximum. Maximum value is under root mu rg. Now, as we go to the next one, banking of a curved road. What does banking of a curved road means? When you are going in a cycle, you are able to bend nicely. But when you are going in a car, you are not able to bend. Had it been bent little bit, maybe this is going little tilted, instead of like this, it just goes little tilted like this, then it could have a more bigger velocity. So the system of raising in a curved path the outer bank, the raising of the outer bank of the road when compared to the inner bank, inner side, by an angle theta, this is called the banking of roads. In a curved path, you will be able to see this side, they will put a lot of little elevation. It will be just nice elevation will be there. You will be able to execute a nice thing. So the raising of the outermost part of the road when compared to the innermost part of the road, so that the negotiation could be safe, that is called banking of a curved road. Please write down this definition. What is the banking of a curved road? So it is the system of raising the outer edge of a curved road above its inner edge is called banking of the curved road. The angle through which the outer edge of the curved road is raised is called angle of banking. This is called angle of banking, and this is called the banking. Mainly it is the system of raising this one, that is called banking. Okay, now we are going to see another derivation of a car going on a circular path where the road is banked. Okay, so take down the thing, take down the topic here, C part of it, A and B and C. Car moving in a circular banked road. A car is moving in a circular banked road. So what will happen? We're going to see this one here. So let us see this topic, car moving in a circular banked road. Okay, so draw this diagram. It is a little complex diagram. Please make it carefully. It's a curved path, and this could be the radius of this one, radius of the curved path, and this is the horizontal, and we are having a banked path. Theta is this one. Now the car is coming in this side. So the way I am drawing the diagram, you can draw the diagram. So this is the way the car is coming now, in a banked path. Now as the banked path is coming, now look at this one, it's already on an elevated path. The path is elevated. So the value of mg acts straight downwards, but the value of r acts like this. We know this one. And what is this one going to be? mg cos theta. And what is this one is going to be? mg sin theta. Known facts. This is a very simple one. But remember, as it is moving very fast, the frictional force will be acting in this direction. This is the frictional force. Here also it will be acting in this direction. So this frictional force also can be resolved into two components. It is looking very much, it's going to be looking very dirty now. Frictional force is also here as theta, resolving two components of frictional force. The frictional force of here and frictional force along this direction. This direction frictional force will be F cos theta. This direction of frictional force will be F sin theta. So you get so many other ways. It is all coming quite different in understanding, right? So even though it is like this, let us try to understand this way. Now since it is coming like this and like this, what you can try to do is mg, and because look at this one, f cos sin theta and mg, and it is better to make a value here like this. What happens here if this is theta here? So this will become equal to r cos theta, and what is this is going to be equal to r sin theta. Alright, So r cos theta and r sin theta. I think this mg sin theta is not this way. It's going to be acting along this direction, so you need not really take that one. Okay, so we have quite a lot of stuff which is then right here. So shall we redraw this one? I'll quickly redraw this one and I will give an explanation. It is better to make this diagram as many times as you can, because drawing this one is not easy. There is a circular path, this is the straight line, this is the banked path, theta is this one, and there's a car coming here, this is a tire, and as this tire is here, and so this guy is riding here, mg acts downwards and r acts like this, which is perpendicular to this direction. Now once r is acting like this, you can make this as an angle theta and give this as r cos theta. If this is r cos theta, what is contributing here? This is r sin theta. Frictional force will be acting like this so that it will not slip away. Frictional force will be acting like this. This frictional force also can be resolved into two components, because this will be theta here and there will be again down component will be there. So what is this value is f sin theta, and this is going to be f cos theta. Hope it's clear now, right? We are not going to take mg cos theta and mg sin theta. You can take that also, but we are not considering here. Please remember that. In that first picture I drew this one, it is not necessary. Mg cos theta and mg sin theta is not needed. So it is better to stick on to the next part of it as reaction. We are trying to do the components. Once this is done, then the derivation becomes quite simple. Please write down. Consider a car traveling on a curved path, banked with the angle theta. Let r be the radius of the curved path. mg acts vertically downwards. Capital R, normal reaction, acts perpendicular to banked road. R can be resolved into two components. R cos theta along vertical opposite to mg, r sin theta along horizontal towards center. R sin theta is towards center. Next one is the frictional force. The frictional force between tires and road acts towards the road, can be resolved into two components. F cos theta is along the center and f sin theta is along the weight mg. Okay, so you got quite a good amount of substance which is being written here. It's all looking quite complex. Now what did we do? F sin theta is acting downwards, mg is acting downwards. F cos theta and f sin theta is going to be acting towards the radius. So f cos theta is along the center and r sin theta is also along the center. So that's what we have defined now. So we are going to make two equations out of that. So the first equation is along the horizontal. Along the horizontal, what other things are acting? F cos theta plus r sin theta, that is going to be equal to mv square by r. Along the horizontal, the force contributes to centripetal force. Next one is along vertical, acts along mg. So what are the things that acts along mg? F sin theta plus mg is equal to r cos theta. Quite simple. Sounds very interesting and easy. Two forces downwards and only one force in the top, r cos theta, exactly opposite to this one. Here two forces are there, it contributes to the centripetal force. Based on this one, we will be just going to quickly see here and there how this could be reversed. mg will take it to the next side, right? So when mg goes to the next side, f sin theta, so it's going to be r cos theta minus f sin theta is going to be equal to mg. So that's going to be the equation number 2 again. The equation number 2 again, it's going to be there. So this is the first equation, this is the second equation. 1 divided by 2, we'll try to do this. So carefully write all of the steps of equation number 1 and equation number 2. F cos theta plus r sin theta divided by r cos theta minus f sin theta is equal to mv square by r upon mg. These two get cancelled out, right? So what you can write it as v square upon rg, you can write. Now in this one, you can make a little bit of adjustments here, trying to multiply and divide, and then you'll be able to get the next equation here. So the next part is dividing numerator and denominator by r cos theta. Mostly you will forget this one, what to do next. Till this one everybody will do. So we are going to divide and divide this numerator as well as divide the denominator by r cos theta. See how it comes. Upon r cos theta plus r sin theta upon r cos theta. I have done the denominator r cos theta upon r cos theta minus f sin theta upon r cos theta. This is equal to v square upon rg. So what will be finally here? F upon r plus everything will cancel tan theta. This is the top numerator. Denominator, what will happen? 1 minus mu tan theta is equal to v square upon rg. Right? So here I need not write mu, I will write it as f upon r itself. Okay, you need not get confused. So f upon r is already equal to f upon r is going to be equal to mu. You already know. So you can write it as mu plus tan theta upon 1 minus mu tan theta is equal to v square upon rg. We need to find out only v. V square is equal to rg bracket of mu plus tan theta upon 1 minus mu tan theta. So what is just v alone? Put entirely into this one. Mu plus tan theta upon 1 minus mu tan theta. This is the final expression. You will be asking, sir, why this such a big derivation? Getting very confused. What is all happening here? Remember this expression. It says, what it says is, in case of a banked road and the car is moving, because of the friction, you can go in a higher velocity. Because it's banked, you need not worry about it. That's what it says. Look at this one. How much velocity it could be there? Velocity could be greater because the mu value will be there. Suppose if mu is 0, no friction is there, you put 0 here. What will happen? 0 if you put, here also 0 you put. It is going to be rg tan theta only. Right? So when mu equal to 0, v is going to be equal to under root of r g tan theta will be there. In other words, tan theta is going to be equal to v square upon rg. You will get, squaring on both sides, you will get this value. But still, it is pretty less. Because of the mu value, it is added here. It's added here, mu plus tan theta. So you can go on a higher velocity, very nice higher velocity you can go. So that's very, very important, how much you are accelerating and going ahead. In case of no friction, only you will get this much in the banked road. V is equal to rg tan theta. With friction, you will get this one. Mu plus tan theta, 1 minus mu tan theta, you will get this one. So with this, the car will be very, very safe. Alright children, with this we close today. So please remember, all the 3 derivations are very important. Draw this one again, do this again. You can remember this expression. I did this one little bit wrong. You can also land up like this. So please remember to do a right diagram and then do it properly. All the best. Thank you.